Welcome back, everyone. This is the last PowerPoint for the RK7 Metallurgy module, and it covers aluminum. Third section, page 3. Aluminum is a lightweight, non-ferrous alloy. Non-ferrous meaning it does not contain any iron. This alloy is 1/3 the density of steel and has one of the lowest melting temperatures at 659 degrees Celsius. As a comparison, steel melts at 1538 degrees Celsius. It's quite a difference. The thin oxide film that aluminum produces is highly resistant to corrosion. Most of the world's aluminum is mined from a raw material called bauxite. Bauxite contains up to 25% aluminum and is mostly found in Ecuador. Aluminum alloys are easy to work with and retain ductility at sub-zero temperatures, meaning it stays workable and formable when it's cold. For more interest, I will post a video link on your Moodle page about aluminum production. Page 5 and 6, wrought alloys and series. Wrought means the material has been heated and worked with tools. The series indicates what has been added to the aluminum. Each of these groups have their own benefit. The two general classifications of aluminum are the heat treatable and the non-heat treatable. In short, this is a metallurgical look at how the alloy reacts to the heating and cooling cycle of welding. For heat treatable alloys, you must be careful of heat input. If it gets too hot, you could lose the strength out of the material. Out of this chart, the 4, 5, and 6000 series are most common. The chart shows the major alloying elements that are added to each series. Page 10, how aluminum is designated. The first digit identifies the main aluminum grouping. For example, 4 is the silicon series, 5 is the magnesium series, and so on. The next two digits show different alloys in the group. This is an extension of the major alloying element in the series. The last digit refers to production form. Production form could be casting or ingots or forgings. And the temper designation indicates how the alloy has been treated to achieve its desired properties. Because of the low melting temperature, aluminum is sensitive to heat treatments. Anodizing and alkali treatments are performed to create a hardened, corrosion-resistant coating. Anodizing increases the thickness of the natural oxide layer on the surface of metal parts. Alclad is a corrosion-resistant thin sheet formed from high-purity aluminum. These treatments give a durable surface finish, and they're commonly done to aircraft parts. Here's the summary for this section. Moving on to page 16. This shows how common groups of aluminum react to welding. The 1000 series group is fairly easy to weld. The copper in the 2000 series group helps to counteract hot shortness. 4000 series has silicon, which is great for weld bead appearance and works good for welding both heat and non-heat treatable alloys. Magnesium in the 5000 series gives this group high strength. It is always best to select filler rods with the same composition as the base metal for best results. Page 17. Before welding aluminum, the oxide film must be removed for best results. This is commonly done with a wire wheel. It's best to reserve a stainless wire wheel and only use it for aluminum so that you do not contaminate the alloy. Most common processes are TIG and MIG. They're both used with an inert shielding gas, argon helium. Stick welding can be done, but it really sucks. I'll let you guys try it in the shop when we get back in there. One of the main problems when welding aluminum is that the base metal does not change color when it reaches the melting temperature. And this stuff heats up real fast. And the last issue here is shrinkage and castings. The shrinkage in castings, it decreases the success rate of repairs. Hot shortness is one of the main problems associated with aluminum. This is a loss of ductility near the melting temperature, and it results in cracking. The alloy 6061 is prone to hot shortness. You can use 4043. It offers less crack sensitivity when you're welding 6061. As mentioned previously, best way to control hot shortness is to match the base metal composition the best you can. If you don't know what it is, usually you use 5356 because of the strength in it. Try to use high welding speeds to reduce heat input. Don't do tack welds without filler metal because they'll just crack. And when finishing a weld, add enough filler to counteract shrinkage so that you don't get crater cracks. Here's a summary for this section. You can pause it as you need to. Last part on page 25. The four main types of heat treatments for aluminum are shown. Annealing, as we covered for steel, restores a soft structure in materials. The temperature for annealing aluminum is 343 degrees Celsius. And comparison for steel, it was around 920 degrees Celsius. So once again, quite a big difference. For stress relieving, bring the material to a temperature of 232 degrees Celsius, or you can peen the weld after you're done welding. Solution heat treatment at 510 degrees improves corrosion resistance, and precipitation hardening happens after solution heat treating by sitting the material out at room temperature. For this, strength will increase rapidly in the first hour, and then over a 1 week time period, it'll slowly increase. The next 3 slides are a summary that covers all the aluminum info. Pause it as you need to get this stuff down. The test on this book is 66 questions. See you on the next one.